All right, we are live. Good morning, good afternoon, and good evening, ladies and gentlemen. I hope that you have had a great day or you are looking forward to a great day and your hair looks better than mine after a couple of weeks of quarantine. The topic of this talk is Aerospike client design and internals. And we are gonna cover a relatively large surface. So after rehearsing this talk myself a few times, I've noticed that because of the surface, the transitions are not very nice. So if I leave some topic unexplored, please feel free to put your questions in the question box, and I will try to answer them during the talk. But if I see that I have passed the point of that question, I will leave them to the end of the talk. I also apologize that I'm not looking at the camera all the time. I'm not a pro broadcaster, so I have a bit of trouble keeping my train of thought while looking at the slides. So first, I should give a small introduction. I'm a member of the Aerospike engineering team since 2014. I'm the original author and maintainer of the Go, Ruby, and Rust clients. And of course, from this, you can tell that I like different languages. And the reason I did them in many languages was I was trying to find out about exactly the topic of this talk, to find out how we can idiomatically implement our clients in different languages and keep them fast and keep them good. And actually this paid off because we noticed some patterns that in some languages were difficult to implement, which we'll get to, and it actually reflected in the clients that we have. So the agenda of this talk is basically what a smart client for distributed database is, which all the Aerospike clients are. We will talk about clustering and partition management, about modes of operation in Aerospike clients, a bit about connection pooling, which is an important part of all of our clients. We will go through command execution pipeline that all of the clients have. We will talk about retry mechanisms and error management, how Aerospike basically knows return multiple records to the clients, and how map and reduce work. We will very briefly talk about wire protocol and data types, and we will finish talking about the clients by talking about the final touches like testing and quality control, and how the community can help us further develop and basically upgrade our clients, and we can take them to the next level. So Aerospike clients are smart, but complex. There is quite a bit of internal logic to any client for a distributed system. And the most important part is how to find out where our data is, so that we can just do one round trip per transaction and avoid every other network chatter, which comes as a surprise, but not many databases and distributed systems actually implement this. There are two modes of operation for each client, which are AP mode, basically the mode that compromises on consistency, but tries to keep the availability of the database and mitigates the partitioning of the database. And also there's a mode that is the other way around. It prioritizes consistency over availability. Depending on the type of our clients, we have synchronous and asynchronous modes. Some, like Go, have only asynchronous modes. The rest mostly have sync and async, and some clients only have synchronous modes. Of course, the client has to track the nodes of the cluster, and all the clients try to help the developers do some of the mostly used workflows like retrying failed transactions based on circumstances and user profiles. And of course, all of the clients handle connection pooling. And to be able to continue, we have to first talk about what a cluster, at least an Aerospike cluster, is. Basically, the easy mode is that the ideal mode is that we have a network that does not fail and does not have any latency, and we have a client that sees every single node with clarity and without any latency, and everything is perfect, and everybody's thinking about going and making a sandwich for themselves. The problem always, of course, is in the reality, which almost everything goes wrong. And in this case, there are multiple things that can go wrong. Especially in cloud environments, a node can disappear without warning, and it can be reaped and recreated on a different machine, even on a different zone by the cloud provider. The connections between the nodes may become slow or completely stop working. And the same can happen between the clients and the server nodes. So the client can actually have trouble connecting and seeing a server node while that same node is visible to other server nodes. And also some nodes may become slower. And the client has to manage the transactions while all of this is going on. And of course, all of this logic is embedded in the client. All of these, the clients actually, to be able to do their job, they have to track the state of the cluster. And that tracking in all of the clients is called tending in Aerospike jargon, which means that if the client is periodically, normally every second, is pinging all the server nodes, asking them for their state. All of the server nodes maintain a state called partition generation. If anything happens with the partition, meaning that the server nodes themselves, for whatever reason, decide that the state of the cluster has changed, they increment this number. And by that, the client understands that it has to update its partition map. A word on partition map. The partition map on Aerospike clusters is basically where how data is partitioned. And this is how the client knows a certain key or ID of each data record, where it is. And of course, depending on the replication factor of the cluster, there is one master record, and there are potentially multiple replicas. And depending on what happens to a certain node, other replicas may be elected as master by the server nodes. And the client has to track these changes and make sure that every transaction is sent to the right node, especially depending on the transaction policy, basically. So if a node goes down for whatever reason, the cluster on the server side tries to mitigate that by electing new masters and migrating the data between each other. And of course, the client follows that flow and keeps itself updated. Now, when we say modes of operation, of course, we talked about what the priority of the client is. So depending on what happens to a node and what is the stated policy of the user, the client decides which node to go to be able to get to the data as fast as possible per the basically SLA of the user, right? And these policies are basically either to go to master, which is normally always for write operations and for a lot of read operations as well. It can do first go to master and then try a prol or try a replica. It can do sequence, meaning that it can go through one by one through master and the rest of the replicas. And one important feature of our clients is that they can actually, because the server supports a rack feature, the client can actually try replicas in the same rack to minimize the cost of going outside of the cloud provider zones, which incurs extra cost. And of course, some can do even random. All of these depend on the mode of operation and the policy and the use case of the user. So different use cases can set these policies differently to get vastly different results. Now, before continuing, I want to actually talk about connection pooling, because this is one of the important things that all of our clients do, and this is one of the things that we do well. And of course, it is the first step in the basically transaction pipeline. Nowadays, the multi-core CPUs are becoming cheaper and cheaper. Nowadays, we have almost consumer CPUs with 64 cores, 128 threads, and with 2 sockets, you are talking about 256 basically CPU threads, trying to munch on the connection pool. And based on our benchmarks, this creates contention. So Aerospike clients do not maintain just a pool, but they maintain a pool of pools for pool of connections per each node. So instead of just having one pool that all of the cores are competing for, we have multiple, depending on the number of CPU cores, we have multiple connection pools that that each of the threads try to get to one of them, and we reduce the contention, lock contention on each of the pools, basically. And of course, each connection maintains, depending on the client, maintains its own buffer. So for example, Go and Rust clients, buffers are owned by the connections. So we avoid also having to use a buffer pool. So there is just one contention for the connection. In threaded connections, of course, buffers are thread local. And in lower performance clients, in some of the dynamic languages, it doesn't really matter because the contention is normally on the GIL, global interpreter lock of the interpreter itself. Now, to just actually talk about the pool and how they are implemented. This is the Go implementation of it, but other clients more or less have the same implementation. So you have a single connection heap, and it's important that it's a heap or a stack because it maximizes cache utilization. And each connection heap is basically an array of single connection heaps. And in the next slide, we will talk about how a single connection is pulled from this. But the important part is to understand that basically a connection heap contains multiple connection pools to reduce the contention on connections. And the logic for each connection pool is relatively straightforward. There is some difference in our clients. Some clients do not care about race conditions in this case. So they just start pulling from Q0, basically from first pool, and just increment it without caring about the race condition. And in this case, that race condition doesn't matter. In some of our clients, people actually compile and test their code, making sure there are no race conditions. In this case, for Go, we have tried to not use that strategy, and we just start from a hint. And this hint is basically the first byte of the key, which is a hash of the key the user provides to the client. And of course, we start from a queue, and we start pulling each queue until we get to a connection, or we find out there are no connections, and we return nil to the user. And this is how we minimize basically the latency and the contention. Um, which brings us to actually that aforementioned execution pipeline. And as you can see, this is not from a real client. This is pseudocode. Different clients have basically the same pipeline, but of course with error management and all of that. But as you can see, first the client has to decide what node to get, and then it needs to get a connection from that node, which we discussed in the previous slides. But then it has to provide a buffer, which is the command that will be sent to the server, then write it to the connection. And of course, because we retry, we also keep count of how many times we have sent a certain command to the server, that we will discuss this a bit later. Then it has to parse the results of what the server is returning, and of course put that connection back to the node and just return. And this is basically a loop. It's not really an indefinite loop the way it is here, but certain number of times this loop will go through depending on the policy that the user has set. Now, how do we get a connection synchronously? Of course, we pull a connection from the pool. If we had the connection, we of course do our transactions. But if we didn't have a connection, we have to check if we are allowed to make one. And this is something that all of our clients do religiously, because the number of connections in the pool, the number of connections in flight, the number of connections that can be created at any given time, and basically the number of failures, all of them are tracked in our clients. And one of the things that we check is if we have created too many connections. But if we still have capacity for any connection, of course we will make one. And that making one is in the same pipeline as the transaction itself in synchronous clients. And there is no way around it. At least there is no easy way around it. So the client actually makes a connection inline, and the timeout of it is a point of contention in itself, but it is controlled by user policy. If the connections, creating that connection succeeds, of course the transaction will continue. Otherwise, in an asynchronous connection system, that creating of that connection is not in line. So a signal is sent to a different thread to make that connection and put it in the connection pool, which on the next retry will be given to whichever command or transaction comes first. And this is one of the points that all of our clients have done meticulously. Now, of course, any type of, in that pipeline, almost every step can go wrong. And there are multiple different types of things that can go wrong, but categorically, either they are on the client side or on the server side. And of course, when errors happen on the client side, the client has to decide if it can go forward or not, if it can retry. And it has to decide, depending on which stage that the error occurred on, and which transaction it was doing, and which mode of operation it was operating in, it will decide if it wants to do retry or not. The server side errors are different, and sometimes the client can retry them, but it has to decide if it wants to retry them or not. For example, if it goes to a master node and the master is not there, or something has changed on the cluster, it has to decide, okay, should I go or not? Because the command was transmitted and it may not be, for example, idempotent. So based on that, and also based on user policies, the clients do track errors, and based on them, they decide if they want to continue or retry the transactions or not. Which, this is that pipeline. So getting a single node from a partition can, based on the key, may return an error because maybe the cluster is in a state of flux, and that partition, for example, the master partition, is still not elected, or the connection has not updated its partition map regarding the master partition. Getting a connection back may result in an error because not only it has to connect, for example, it may pull a pool and there are no connections in the pool. Maybe it will have to go create that connection from the server node, and it cannot see that server node, or it times out, or maybe the authentication fails for whatever reason. This also can return an error. Writing a buffer, sending a message to the server may also result in an error. Parsing the results back from the server may result in an error because the connections may time out, or the data may be corrupted while being sent. So there are multiple stages that things can go wrong, and the way that they are communicated to users are different based on our clients. Some clients do return errors. Some clients use exception management to do that. But no matter what, normally you get a result code, and the client lets you know if it's sure that the transaction failed, or it is in doubt because maybe it sent a write request to the server. The server actually applied the transaction, but before informing the user, the connection went down. And the server basically has to make sure that it is tracking. The client has to make sure that the user knows that maybe the transaction went through. And of course, there are different error codes for different clients. And this is, for example, an example of our Java client. And this is the exception that it returns, which different information about the transaction are embedded in this exception. Each transaction, of course, in Aerospike maybe most of the normal transactions are single record. You either change a certain record, delete it, update it, or put a new record in the database. But the server supports multiple types of streaming commands, meaning that a command returns multiple records. And of course, in such situations, depending on the language and idioms of that language, we have different ways of getting the data back from the server nodes to the client. So normally, these are either threads or green threads or Go routines, which parse every record and then return it to the user either via a queue, a channel in Go, for example, a callback in some other languages. And then the user either pulls these information, for example, from that queue or channel, or of course, a callback is a different thing, and the client automatically will know that a new record has returned. And of course, here error management is more complicated, and different types of basically commands treat errors differently here. For example, some users, if they send a batch request, meaning that they want multiple records, they may want to get partial results, meaning that if one server node didn't return the data, they want to make sure that, for example, the others that sent the data back, they get the records. Of course, they want to also see the error regarding that failed node, right? And it gets complicated because maybe multiple nodes will error out, and the client has to decide how to merge these errors to let the user know. But this is not the only type of streaming, basically, commands that we have, which are normally scans and queries. The more sophisticated type of streaming commands are map reduce commands. Aerospike supports map reduce via its UDF. There are certain types of UDF that you can use that help you execute a map reduce in the database. And the way this works is basically it runs a certain number of tasks. So it filters, it runs a UDF on each record. That record maybe it has to pass a filter. If the filter applies, maybe there is a map stage that the record will be transformed into something that is usable, and then multiple records will start being reduced and merged with each other on the server side. Of course, this scheme has a problem that when you have multiple nodes, that one node cannot reduce all of the records. So it will send partial results to the clients to be reduced. And the final stage of reduction is, of course, done on client side. And most of our clients, not all, but most clients support Lua libraries on client side and run that last stage of reduction on the client. Now, a short, basically, let's talk briefly about the wire protocol in Aerospike. Messages in Aerospike are basically just header and message, and the header basically has some metadata and message size. And each message itself may have metadata, message size, basically header, and then a payload, which can be a record or multiple records. And the system has been designed to be as small as possible and as efficient. And by efficient, I mean CPU-wise, it is designed to be as efficient as possible. And it's very close, not exactly, but very close to the format that the server also keeps the data. Of course, when we talk about data, there are beautiful primitives. There is no data, integer, there are floats, strings, blobs, and GeoJSON, which are very simple data types. And they look beautiful and very simple until we get to the real applications, and suddenly everything becomes complicated. So Aerospike also supports complex data types like lists and maps, and lists and maps can be sorted on the server side, and different operations on each of them can be done via the client. Now, lists and maps on the client side, and also to a certain extent to server side, are basically, at least currently, message pack data. Right, they're encoded in message pack. Message pack is very size efficient, and it is a bit CPU heavy, and it needs different tricks in different languages to work efficiently, because some languages you can have generics that the types of the data can be undefined, and based on the data that is passed to them, they can be they are compiled differently and allow the encoding on compile time. Some languages do not allow this, and the client has to use reflection. And there has been a lot of work done in our clients to allow more efficient ways of implementing this, so that it avoids reflection or avoids as few memory allocations as possible, especially because most languages nowadays are garbage collected, and memory allocation can be in a high performance systems with millions of transactions per second. Memory allocations rapidly become a bottleneck and the cause for latency. Most of our clients always records as hash maps. The objects, complex objects, need serialization and deserialization, and of course there has been a lot of work done to make this more performant. Of course, any type of software requires a final touch. The way that we do quality control and testing is that we do, of course, unit tests like everybody else against single node and multi-node clusters. And remember, we have a community edition and an enterprise edition. So all of them go through tests. And also we have a CI system that runs the same tests against far more configurations that developers can do on their own machines. And To help vet some of the external contributions, we also run them on an external CI. And still, we need discipline, and we do we look at each other's code every once in a while to make sure different clients are done right, and certain quality points go into the client code. A word about our clients. Of course, when we talk about clients, clients are actually programmed by different developers in the company. And of course, depending on the language and the use cases for them, they are different tiers. And of course, most of the clients are tier 1 when it comes to supporting them. But some clients, which are not used as much as the other ones, are tier 2, meaning that we support them, but we look for community help for them. And of course, there are tiers of performance. So compiled languages, especially compiled statically typed languages, are the faster ones. But of course, the other ones are not far behind, except that, of course, dynamic languages are a bit slower than the rest. Now, just here, I would like to actually point to some statistics regarding our clients. The community are helping us quite a bit with either feature requests, pull requests, reporting issues, and all of our clients are active on GitHub, and we interact with the users on GitHub, regardless of the server edition that they are using. And of course, if you want to get involved, the best place to report bugs, request features are through the provided channel for commercial customers. Otherwise, clients library GitHub repositories are a good place. We also, if for just asking questions about anything, our forums are a good place to look for either asking others about your problems, about idioms of use, and of course we have a good knowledge base regarding most used use cases in case you come across something that you think that somebody else might have done. You can also get involved with our libraries by just making pull requests on GitHub, and we do normal open source development. So basically, it's just clone the GitHub branch, change tests, make a pull request. After a lot of discussions, probably we will merge your pull requests, and we will be happy to. And of course, pull requests will automatically be tested against different CIs, so and different VMs in different places. So don't worry, the bar is not high. You can easily get involved, and we will help you to get pull requests. Some of our users have made pull requests of thousands of lines of code. Just a word on deployment of our clients. Some cloud providers do not allow certain libraries linking styles. Some require only static linking, for example, for some languages. They have unpredictable CPU allocations. They may not warn before terminating a node and reallocating it. So there are no graceful shutdowns for some type of apps, and require dynamic seeding. So you don't know how, during compile time or just during runtime, you cannot be sure that the seeds that you used in the beginning persist. Both the client apps and the server nodes may disappear at any given time. So all of the clients are designed to be able to mitigate this and not lose data. So thank you very much.